Johan, please.
Thank you for the introduction. Is this supposed to go away? So indeed, thank you for the introduction. And as introduced, so this talk is in the context of the Remade.ARI project, which aims to support the sustainable and circular economy. And we will do that by supporting the materials characterization for sectors such as electronics, batteries, materials, vehicles, packaging, plastics, textiles, food, and so on. And there are various advanced research infrastructures in Europe that aim to support this. We'll come to that in a while. But today, the purpose is to talk about ion beam analysis and introduce the technologies that are related to that. So personally, I'm active at IMEC, which is an international research institute performing research with global leaders in microelectronics industry like TSMC, Samsung, Intel, and so on. We are doing research towards the novel integrated circuits devices that we will find in our mobile devices and computers within 10, 20, and 30 years. And at IMEC, we have a long history doing ion beam analysis on these materials together with the KU Leuven. We have more than 40 years of experience with ion beams to study these materials. So the KU Leuven, the University of Leuven, is just across the road opposite to IMEC. So IMEC is doing research on microelectronics components. And what you see here is the site, the campus of IMEC in Leuven. And what you see on the left is the ballroom type class 1000 300 millimeter clean room, which is located on the main location of IMEC. So this is a ballroom type clean room, which has the size of a soccer field. So to frame this presentation here, I would like to introduce you the Radiate Network, which is an association of multiple partners bringing together advanced research on ion beams in Europe. And in fact, this was originally funded by the European Union to run from 2019 with the aim to bring together the knowledge and to inspire each other to advance the field of ion beam analysis for materials characterization and modification. And today I will not talk about ion beam modification. That might be the subject of another presentation. I will mainly focus on ion beam composition mapping and imaging together with ion beam analysis spectrometry. From these, there is one activity that I will not talk about, and that is accelerator mass spectrometry, which is a technology which allows to analyze the isotopic abundances in materials that are probed from different origins. And that's a technology that allows you to, for example, date materials or find forgery and so on. I will mainly focus on ion beam composition mapping and analysis of materials for technological applications. And when we talk about ion beam analysis, we think about the crystallographic, the elemental, and the isotopic composition. We will do this with ion beams that range from energies in the range of 10 kilo electron volt to 10 mega electron volt. And this probably needs a few words of explanation. So on this slide, I show the penetration through silicon for the different probes that are, or for some of the probes that are being considered in the Radiate project. In the REMATE project. So on the left here, you see that X-rays have a large penetration through silicon. This, of course, depends on the energy of the photons. The larger the energy of the photons, the higher the penetration depth through the material. The electrons, on the other hand, have a smaller penetration depth and therefore can have a better sensitivity to near surface phenomena. And then on the far left of this graph, you see that the hadrons, like protons, alpha particles, and so on, have a much smaller penetration through the material. This will have large consequences in their behavior, in their interaction with the material. The high stopping power of these particles, when they are energetically hit towards the sample, will make that these particles, through their interaction, will be much more sensitive to near surface interactions. You also see that in order to have some penetration into the material, you need a beam of at least around 10 kilo electron volt. And we speak about 10 mega electron volt to have a penetration depth of several microns. So it's important to consider that the range of ion beam energies that we will deal with is of the order of 10 kilo electron volt to 10 mega electron volt. The characteristics that we will probe are substantially different depending on the energy that the primary ions have when they hit the sample. At the lowest energy that we were talking about, the ions will mainly hit with the outermost surface of the sample. On this graph here, you see the representation of a helium ion microscope, for which the ions are accelerated to about 35 kilo electron volt. And the ions are, with a special technique, you have a very narrow source, or a very point-like source of helium ions, and they can be directed towards the sample very much like an electron microscope. The advantage of this technique is that these materials, or this technique, is very surface sensitive and not so much damaging to, for example, organic materials. So this is why helium ion microscopy sometimes is used for the analysis of organic materials. At the same time, this technique has a very good depth of focus, and therefore it can be applied to look at the morphology or the surface of materials. One property that distinguishes this technique very much from electron microscopy techniques is that it is not very much dependent on the surface charging of the material. So this technique, this imaging technique, can be used for the imaging of highly insulating materials. Now, this approach is not very much a large infrastructure technique. For that, we need to go to higher energies. And one of the techniques that applies or that uses higher energies is medium energy ion scattering. We speak about medium energy ions when the particles have energies between 100 and 400 to 500 kilo electron volt. So for that, you need an accelerator which can go to these voltages. And here you see the picture of a implanter-like accelerator, which is hosted in Uppsala in Sweden at the Angström laboratory, where particles can be generated in an at an ion source inside this enclosure, which can be brought up to 100 kilovolts. Definitely, these ions will penetrate already a little bit into the material. This is what you can see here on the left. The helium particles are projected onto a sample of silicon, which is coated with 2.7 nanometer of nickel on the silicon substrate. After this sample is heated to 540 degrees Celsius, you see a distinct distinctly different characteristic of the spectrum. I will explain the spectrum in more detail with regards to the higher energy, but you can already see that the spectrum is quite different from the spectrum that was obtained in its original state. So from fitting and analyzing the spectral shape of the particles that are being scattered on the sample, you can derive something about the depth profile of the nickel on this silicon sample. Important is also that the backscattered particles in such a medium energy ion scattering experiment have much lower and have rather low energies and can be treated with electrostatic and magnetic fields easily. And this allows to obtain full 2D maps of the particles as a function of energy and angle of exiting the sample. So here you see such a 2D map as a function of the angle for the two angles as the particles exit from the sample. And you will see here that after the sample has been heated to 540 degrees Celsius, that some dark spots appear. This has to do with the blocking of uppermost atoms, avoiding that the scattered particles end up into the detector. This is a phenomenon which is recognized as a blocking, or it's termed blocking phenomenon. So this blocking phenomenon can be related to the diffraction of X-rays, or is very similar to the diffraction of X-rays emitting from a sample. So you can understand that these blocking, the points of the blocking regions in the backscattered spectrum tells you something about the crystallographic orientation in the sample. And this was smartly used to the benefit in the group of Grenoble, where they investigated the crystalline structures of nanodots which were grown on an aluminum nitride surface. You can see here that a dot of 3 nanometer can be studied with this technique, and even the crystallographic orientation can be derived. In this research, people made use of the mass selectivity of the scattering in this experiment. And they could see that the crystallographic bending depends very much on the depth with respect to the thickness of this nanodot. So you see that for these mice spectra, you are quite limited to a depth of about 5 nanometer, but in practice, we experience samples that are much thicker than that. And to probe these larger depths, we need higher energies. And then we end up with the large infrastructures as we talk about tandem accelerators that you will find at several spaces, several locations within Europe. You see here the size related to the size of a human man. So we are talking about a hull, the size of an experimental hull to host such an experimental setup. And the typical setup is composed of a helium ion source or another ion source for heavy ions. Then these ions are brought into the anionic state, so you add an electron to them, and then you accelerate them typically to the positive terminal inside the accelerator. The acceleration voltage in the center of the accelerator is typically of the order of 2 to 5 megavolt. So you can understand that to achieve these high voltages, you need to insulate the terminal inside that tank with respect to the outside world. Otherwise, you would have discharges. And this is achieved by putting a high dielectric gas around this terminal so that you can avoid the discharges. And this is also why such an infrastructure has such a big size. So once you have accelerated the ions towards the terminal, a trick is used to convert the helium minus, so the anions, into positive ions, which are then further repelled from the positive terminal in the accelerator. And the energy of the exiting ion is double the energy of a single acceleration stage. So if you have 2 million volts in the center of the accelerator, the exiting helium particle will have an energy of 4 mega electron volt. One of the advantage of such a system is that by stabilizing the accelerating voltage to about 1 kilovolt, you can achieve very narrowly defined energies for the exiting particles that are emitted from the accelerator. And this is why such an electrostatic accelerator can be used to energy dispersively measure the interaction of the particles with a sample. So on the one hand, much of the effort goes into the installation of the accelerator, but on the other hand, also much work is done to optimize the end stations, to optimize the experiment and investigate the samples. And the different laboratories within Europe are each of them specializing in one specific experimental geometry or detection system to optimize a specific property of detection. And as you see here on the right, this is a microprobe setup, which is, for example, hosted in Atomki in Hungary, and it allows you to define a beam spot onto the sample of the order of submicrometers. So in the following slides, I will present you a few key technologies that are being used to probe the backscattered or the emerging radiation and particles that emit from the sample during the scattering of the particles on the sample. So the most well-known technique in ion beam analysis is probably Rutherford backscattering spectrometry. And let me say a few words about it. So the basic idea already identified and recognized by Rutherford is that when light particles are impinging on a sample, then there is a small probability that this helium particle will be scattered on the nucleus in the sample. The probability of backscattering or scattering on the nucleus is extremely small if you compare that the cross-section of the nucleus is very small compared to the total size of the atom. But if it happens, there will be a collision, elastic collision between the positive charge of the incoming ion with the positive charge of the nucleus in the sample on which you scatter. And in that specific case, the elastic scattering will lead to a backscattered particle, which can be detected, for example, in a semiconductor detector. The advantage of such an experiment is that the scattering, both for the energy as well as the probability of the scattering, are fully determined by classical theories as you would apply to estimate the scattering on a billiard table. So the heavier the particle on which you scatter, the higher the backscattered particle energy will be. And this is also what we see here on the right. We have, in this experiment, we have 1.5 mega electron volt helium particles impinging on a stack of thin films of copper, silver, and gold deposited on 10 nanometer of silicon oxide. You can see that the energy of the backscattered particles on a gold atom, on the gold nuclei, is much higher than the energy of the backscattered particle on lighter elements, like, for example, silver, copper, silicon, or oxygen. And these things can be perfectly calculated in a classical way. So this leads, if you count the incoming helium particles, this leads to a reference-free quantification of the number of atoms that are in the sample for a specific species. You also notice in this plot here that the sensitivity to the light atoms is much lower as compared to the sensitivity to the to the heavy atoms. So you see that when you scatter on a gold atom, the scattering cross-section is much higher than, for example, the scattering on a silicon atom. This can be understood because the cross-section or the diameter of such a nucleus for gold is much bigger than the cross-section or the diameter of, for example, a silicon atom. So you might wonder how we are using these technologies. Well, let's give an example for such an application. In this specific example, we are investigating a mesh of nanocarbon tubes that are organized in a fabric which is of the order of 15 by 15 square centimeter. We all know that these carbon nanotubes are extremely strengthful, so they can withstand really mechanical stresses. The attractiveness of such a pellicle or membrane is that on the one hand, it can protect material particles to go through, but on the other hand, the thickness of such a pellicle is extremely small. And people are considering such a pellicles to use them as a protection for the EUV mask in EUV lithography. The challenge for the application in this environment is that these materials must have a high transmission for the extreme UV light. So these pellicles have to be made as thin as possible. But on the other hand, there's also a very harsh environment in this EUV lithography, in the EUV lithography tools. For example, there is a lot of ionization, and the radicals inside that tool are attacking the nanofiber, which is posed here. So there is a lot of research going on in characterizing these materials. And on the right here, you see an actual RBS experiment on such a pellicle. You see that we are very sensitive to the carbon, even if this layer has an effective thickness or an equivalent thickness of the order of 5 nanometer. On the other hand, you also see that due to the fabrication, there is some contamination in this material. And it's very important to understand which kind of contamination and how much of that contamination is present in the sample. And you see that with RBS, with Rutherford backscattering spectrometry, we are very sensitive to even minute amounts of contamination in such a pellicle. The impurities of, for example, zinc are of the order of 20,000 times less than the thickness of the carbon. And still, we are able to quantify these materials. So this technique is very supportive in the further development of these pellicles that are being used for practical applications. Now, there is one thing that I didn't talk about, and that is the fact that these particles, when they penetrate into the material, they also lose energy. And then we come to the concept of stopping power. This was one of the things that I discussed in one of the previous slides, where I was talking about the penetration of ions in matter. So when a particle penetrates into the material, it will lose energy. And unlike photons, they are not absorbed, but simply lose kinetic energy. So when a particle penetrates, for example, a few nanometers deep inside a sample and is emitted, you will observe these samples as having a lower energy. And let's consider ions that are being emitted from within the silicon substrate. You see here that as you go deeper into the sample, you will have more and lower energy. So in fact, you can probe as a function of depth the number of atoms in the sample. The depth resolution can be quoted as the resolution with which you can measure the energy differences. And in practice, this is of the order of 1 nanometer. The full analysis depth is twice the penetration depth. And this is of the order of 1 micrometer for practical applications. And the accuracy is of the order of 0.1 atomic percent. And near the surface, we have a sensitivity of 10 to the 12 atoms per square centimeter. So how can we use this technology in practice? How can we use the energy loss of ions in matter to our benefit. And here I use an example of studying nanoparticles of the order of or less than 50 nanometer high, built of silicon oxide, which are grown on a tinitride buffer layer. And in the microelectronics industry, there is a lot of effort going on in the area selective deposition to aid lithography to have better nanostructures, helping to make smaller devices for the microelectronics industry. The great challenge for area selective deposition is to deposit the material in certain areas, as for example, on the metal layer, and not on, for example, sacrificial or other spacer materials. So here the aim is to deposit the material in between the silicon oxide fins, and not on the silicon oxide fins, but in between the silicon oxide fins. So how can we characterize these materials? You see here that, for example, in a TEM, you see that there is a small dot, which might indicate that there is a small ruthenium deposition, but it's very hard from TEM to quantify these materials. So let's do a macroscopic experiment with a ion beam, which has a beam size of the order of 1 millimeter, in which we impinge almost vertically the ion beam. We put the detector at a shallow exit angle, and we make use of the energy loss of the ions when they penetrate through the silicon oxide fins. You can understand that when particles are being scattered on the ruthenium on the top, then they will not lose excessive energy by going through the silicon oxide fins. On the other hand, when you scatter on the bottom of the samples, you will lose a certain amount of energy before you go to the detector. And this is exactly what we observe when we look at the energy spectrum for ruthenium on such a sample. You see that it is composed of a signal at a lower energy, which stems from this ruthenium signal, which is coming from the bottom of the fins. And besides of that, you also have a signal from the top. So by quantifying these amounts, the contributions of the three areas, we can quantify the areal density for the sides, the top and the bottom. You can see that there is a lot of ruthenium at the bottom, while there is less ruthenium deposited on the top and on the sides. Remarkably, we are sensitive to very low amounts of ruthenium, for example, at the side walls. And we can quantify them. This helps us to optimize the deposition processes. And it can help us to produce samples that are looking more like this and less like this. So it helps a lot in the further development of future IC devices. A last technique which I would like to mention with respect to Rutherford backscattering is channeling. So this is a technique where we are aligning the sample with the crystalline axis along the incoming or exiting axis of impingement of the ions, and it allows us to determine the crystalline axis of the sample under investigation. Now, if you would have a little bit of oxygen on the surface of such a sample, it would be superimposed onto the signal of the very intense signal which is coming from the substrate. And this is, you could say, a limitation of Rutherford backscattering spectrometry. And therefore, people in the past decades have developed elastic recoil detection analysis. So in this approach, instead of coming in with a light ion, you come in with a heavy ion. And instead of looking at the scattered particle, you will now look at the emitted, we call them the recoiled particles, out of the sample. Different from SIMS, you will not sputter the sample layer by layer, but you will, in a stochastic and statistical manner, eject samples from all depths in the sample. So you will statistically inject an atom from the top and from deeper inside the sample. The amount of scatterings or recoils is so low that during the experiment, you can still consider that the sample is being unchanged. One difficulty that you could recognize is that when you have different types of ions being emitted from the sample, and they have also different energies because they emerge from different depths, that you don't know which ion species is coming from which depth. And for that, to overcome that limitation, we have a two-dimensional data acquisition which records both the velocity and the energy of the ions, from which you can readily recognize the quadratic behavior which is related to the mass of the emerging ions, of the recoiling ions. At the same time, the energy dependence gives you a measure for the depth at which this scattering occurs. But for the rest, all the kinematics are very similar to what we have seen in, for example, Rutherford backscattering spectrometry. By analyzing these data, we can reconstruct the depth profile, which is plotted here. So you have the atomic fraction in absolute numbers, 10 to the 15 atoms per square centimeter as a function of depth. So with this technique, you can measure the light elements in the sample with a sensitivity of the order of 0.1 atomic percent and a depth resolution of 10 nanometer. And it's important to mention again that this is an absolute measurement. By measuring the incoming particle fluence, you can determine the absolute amount of particles or atoms that are in the sample. So let's give a few examples on this approach as well. So one of the technologies that are recognized with respect to the circular economy is the wafer-to-wafer bonding. So there is a lot of effort going on in optimizing these processes to make the fabrication of microelectronic devices as efficient as possible. And one of the main challenges is to understand what makes these two wafers to bond to each other. And here you see a depth profile of exactly this bonding between the two wafers top to top. And you see that you have the different elements like nitrogen, carbon, hydrogen, and so on, and that at the interface an oxide is formed. And this is a property that you probably also could probe with electron microscopy. The differentiating property that we can also probe here is the characteristics of the hydrogen depth profile. Another important application for the circular economy you could recognize is the application of lithium-ion battery materials. And there have been neutron activation studies and also ion beam activation studies that have led to this picture of how a lithium-ion battery actually is being charged. And one of the key technologies in such a material development is the development of the electrolyte. And you see here that with elastic recoil detection analysis, we are very well capable of mapping the depth profile of the different constituents like lithium, hydrogen, nitrogen, and phosphor in these electrolyte materials. And it helps us by understanding which materials are where, it helps us to further develop these technologies. A last technology which relates to the circular economy and elastic recoil detection analysis is the analysis of membranes. And this is an example where chlorinated membranes deposited on a support are being used to desalinate water in order to make drinking water applications. And you see here, for example, that the chlorine, which is found in this chlorinated polyamide, can be distanciated or distinguished from the support material. This characterization also helped people to further develop these technologies. And this is a characterization that was done at a high energy accelerator in Munich. So as a third technology to probe the interaction of energetic ions with with material, would like to say a few words about particle-induced X-ray emission. So the idea is that a very light ion impinges into the sample and makes an empty or excites an electron from the electron shells. And when a higher energy electron falls back to the lower energy, an X-ray will be emitted. This process of activation, in fact, is very likely. It's much more likely than the processes that we have seen so far. So the cross-section being very high, this is also a very sensitive technique. And you will, or many people will recognize this as being akin to X-ray fluorescence or, for example, energy dispersive X-ray spectrometry in excited by electrons. The difference from the other techniques is that this is a very low background approach. On the one hand, the advantage of PIXE is that the particles emit very low Bremsstrahlung radiation. The Bremsstrahlung is induced by the change of the velocity, and the change of the velocity of this particle when it is transmitted through the sample is much lower than, for example, for electrons, which are much lighter atoms or much lighter particles as compared to these heavy protons. And the second advantage of PIXE is that given that the energies of the incoming protons are very high, you are also capable of exciting very high K energies or K-line energies. And that is why we are capable with PIXE to analyze high Z materials with proton-induced X-ray emission. And this technique is often combined with microprobes to characterize the material depending on the location. And here I quote two examples where PIXE has been applied to investigate, for example, materials for construction. On the left, you see the PIXE spectrum of mortar. So this is Portland cement. And the idea there was to study the influence of the environment on the stability of the Portland cement. And one of the factors that is very important for the stability of the cement and the longevity, the lifetime of the cement, is the penetration of the chlorine. So this study, which was done at Surrey University, shows that the chlorine can penetrate as a function of depth, as a function of time. Another application of PIXE is the mapping of the different elements laterally. So here you will use a microprobe and then scan over the sample to look at the different constituents, for example, calcium and magnesium in food materials. So the last technique, I would like to say a few words about nuclear reaction analysis. So in this approach, you will come in with a light ion typically, and you will excite the nucleus with a nuclear reaction, similar as what you would do with neutron activation. And you can look then at the particles that are being emitted or at the gamma rays that are being emitted during the de-excitation of the excited nucleus. And sometimes these processes are very narrow in energy. So if you then, with the electrostatic accelerator, tune the energy to an energy which is above the nuclear reaction energy, then the ion will first lose energy while penetrating into the material until it reaches the resonant energy. So if at this specific depth, the ion, for example, the proton, reaches the resonant energy, then it will probe the amount of atoms that are present at this specific energy. And the response, for example, in terms of gamma rays or other kinds of residuals from the nuclear reaction, the intensity, the yield of the number of particles that you detect are a direct measure for the concentration of that specific isotope. So here I gave the example of hydrogen impinging on the sample. Depending on the energy and the particle type, you will excite different nuclear reactions. So for each isotope that you want to probe, you can select a different incoming particle or energy, and at the same time, you are very selective to that isotopic material. So by using also, by benefiting from isotopically enriching your sample, you can also look at specific regions of the sample. One example I would like to highlight here is, again, the sensitivity to the profiling of hydrogen, for example, in photovoltaic materials. So when you come in with a nitrogen 15 ion beam and you impinge it on hydrogen, you will excite gamma rays that can be very selectively measured. So by tuning then the energy of the projectile and projectiles, for example, here you tune the energy of the nitrogen 15 atom ions incoming onto the sample above the 6,385 kilovolt resonance, you can probe the amount of hydrogen in the sample very sensitive. And just to compare this with the other technique that I mentioned earlier, this is the depth profile, which is obtained with elastic recoil detection analysis. You see here that the statistical uncertainty is much lower as compared to elastic recoil detection analysis. On the other hand, with the nuclear, nuclear reaction analysis, you only probe one specific isotope at a time, whereas with elastic recoil detection analysis, you probe all the elements together. But it gives you a very isotope selective probe for the depth profile in this example for hydrogen with a very good sub-nanometer depth resolution. So to summarize, I hope I have given you a few ideas about what can be done with ion beams. I have shown you that with RBS, we have a very good absolute quantification, very good depth sensitivity, site selectivity, and a very high sensitivity down to 10 to the 12 atoms per square centimeter. I also have given you a flavor of the application of elastic recoil detection analysis, for example, for photovoltaic materials or for membranes. I've shown you that we can use ion beams to do mapping. For example, we can map the constituents in organic materials or in art or in construction to look at the material composition as a function of lateral position. And I also have shown you that with specific isotope selectivity and making use of nuclear reaction analysis, we can look at very specific problems and try to find specific insight into the behavior of the materials. And last but not least, I would like to come back to the context of this presentation. So I'm very glad that I can represent here the work that is agglomerated in the RADIATE project or in the RADIATE consortium, which constitutes multiple research infrastructures in Europe. And each of these infrastructures has its own capabilities and strengths. You could imagine each of these infrastructures a specific beamline comparable to a synchrotron beamline, but in our case, they are dispersed all over Europe. I have given you an insight in what can be done with the ion beams in terms of crystallographic, elemental, and isotopic composition determination. And I hope I have explained to you the need of using energies in the range of 10 keV to 10 mega electron volt energies and why we need such big infrastructures. I would like to thank also the funding agencies, especially also my employer IMEC and the University of Leuven, which hosts me. And last but not least, I would like to thank the REMADE project for enabling this, and thank you for your attention. I thank you.
Many thanks, Johan, for the nice and didactic presentation. So yeah, please, for audience, if you have a question, please type it in Q&A box. Meanwhile, maybe I will start with one question, Johan. So you presented one slide on elemental mapping in a spinach leaf. So could you then elaborate more on the application of ion beam analysis for organic materials in general and extent of damage to the sample?
Um, so um, I think the main advantage of this approach is that you have a very high sensitivity to the material or to low amounts of material, as you see here. This amount of chlorine is subatomic percent. It's in the ppm regime, and the same can be reached here. The um, the content of materials like magnesium and calcium are very important in the food industry and teaches a lot about how the food or how food is taking up the different constituents that are, for example, being provided in the soil or in the air. So this leads people this could help people in biology and in medical environments to better understand how these biological processes happen.
Okay, thank you. So yeah, I don't see any other question in the chat box, but I suppose people can. Yeah, I do see one. Uh, Thank you for a very thought. Okay, PIXE can detection. PIXE can detect low-Z elements. How can we make them detectable? Any detector limitation?
So maybe a slight correction. So the PIXE is capable of also detecting the low Z elements like yeah, boron or you name it. The limitation is that if you also have a substrate that on the one hand, you will have a huge peak of the substrate signal, which can mask the signal of the low Z element. Um, and um, um, and on the other hand, also, if you have a substrate, you will have also some Bremsstrahlung radiation. The Bremsstrahlung radiation is much less than what you would find with, for example, electron beams. The substrate signal is a property yeah, of the principle of the experiment, but it could be overcome by, for example, wavelength dispersive PIXE. This is one of the approaches. I didn't talk about it here, but it's one of the approaches which is being highly investigated uh, in the ion beam, in one of the ion beam centers. So by using a wavelength dispersive detector, it is possible to selectively measure the low Z elements.
Okay. So we have another question popped up. So this is from Jakub. Thank you for a nice talk. What are the limitations regarding the sample environment, vacuum, liquid, and so on?
Aha. Thank you. So um, for techniques like Rutherford backscattering spectrometry and elastic recoil detection analysis, there are definitely limitations to the sample environment in the sense that the backscattered or emitted particles will be highly yeah, um, deaccelerated by the environment if they are exposed to, for example, atmospheric pressure. But in the case of particle-induced X-ray emission, we face much less of such a limitation. So in this case, we are coming in with very light particles like protons that can um, that can penetrate several centimeters in air. And the example which is given here, which is the setup at, in Portugal, shows that you see here that a piece of art can be put in place in atmospheric pressure in front of the microprobe. And this is also an approach which is pursued at, for example, the Louvre in Paris to study pieces of art. So in that case, the light ion can penetrate like 10 centimeters of air. Typically, we enlarge the amount of helium in that environment to make it as minimal as possible. But the emitted X-rays can be detected with an X-ray detector, just as you would do with X-ray fluorescence spectrometry. So, in fact, this photograph illustrates that also experiments can be done in air.
Okay, thank you. So yeah, we have a comment. So there was actually a comment for light elements. Charged particle activation works much better than PIXE. And we also have PIGE and etc. for fluorine.
Yeah, correct. I don't, this is a correct statement. So yeah. Indeed, for the light elements, nuclear reaction analysis or PIGE, which probe the nucleus, can be extremely sensitive. This is also what I've shown. It would never be possible to probe hydrogen with PIXE. That's impossible. While with nuclear reaction, this is possible. So yeah, I fully subscribe to that statement.
Okay, thanks. So I don't see any more question in the Q&A box. So maybe, yeah, people can still forward you questions or mail you after the presentation. So I have still two slides to share with you. So Johan, could you please stop sharing? Many thanks anyway for the presentation once again.
Thank you.
So yeah, we do have a survey. Please support us improving our next webinars. So the link is available in the chat box. For those replaying the webinar through YouTube, you can find the link to the survey in the description. So I would like also to advertise our next webinar, so which will be on 28th of July. So our speaker would be Dr. Dimitrios Angelos from Ford, with the title Mobile and Remote Analysis of Materials Using Laser Spectroscopy. So we are, I think, much on time. Many thanks for your participation. And we are looking forward to meeting you in the upcoming webinars. Thank you and goodbye.
Bye-bye.